Okay, hi everyone. Thanks a lot to Dirte and all the other organizers for giving me this opportunity. I'm really sorry I didn't manage to be there with you. I really would like to be there. And I'm sorry that you have to attend yet another online meeting, and I'm sure you're enjoying the in-presence one. So nevertheless, I thought I'd take this opportunity to show you what we have been doing in this field of muonic atoms, also the latest things we have done. So let's start. So what are these muonic atoms or ions? So first of all, you can take an atom and make it more exotic in that you replace one electron with a muon. Okay, but what we're going to do today is actually to look only at hydrogen-like systems where there is just one muon orbiting a nucleus. Okay, so and because of the fact that the muon is so much heavier than the electron, it orbits much closer to the nucleus, and as a consequence, it is very sensitive to nuclear physics. And this is the reason why a nuclear physicist like myself is actually interested in looking at these systems, because you can use them as a probe for the nucleus. And in particular, you will see that you can extract very precisely the nuclear charge radii by doing measurements on these systems. So what I'm going to mostly discuss is the Lampshift, which is the splitting between the 2p and 2s of this hydrogen-like system. And as you know very well, you cannot explain the Lampshift in the Bohr theory. You cannot explain even in the Dirac theory, in the relativistic framework, because the 2p and the 2s are still degenerate. What you need to do is to introduce quantum electrodynamic effects before you start seeing this splitting. And that is most of the story, but it's not the whole story, because if you want to measure this very precisely, at some level, you need to take into account of the so-called nuclear structure effects. Basically, the nucleus is not really a point-like object. It has a finite size, and it also has an inner structure. It has internal degrees of freedom, which can be excited. So the latter contribution gives rise to something that we call polarizability. And to give you an idea, you can look at this movie. Basically, the muon creates an electromagnetic field, which, so you have this nucleus, which is embedded in this electromagnetic field, and it can be excited. The protons will feel that. And the consequence is that there will be a tiny difference in the energy levels of your atom or ion. Okay, so that's kind of the physics we are going to discuss. Now, a few words on how these systems are experimentally investigated. That's not what I'm doing, but my colleagues are doing that. And this figure was given to me by Randolph Paul, who is one of the main person in the CREMA collaboration. These experiments are done, for example, at PSI, where they've got a muon beam. If, for example, you want to study muonic hydrogen, you would shoot this beam on H2 gas, and then some of these muons are captured, but in the very high excited states. Most of them fall down to the 1s state, but just some fall decay down to the 2s state. So those are the ones that you're interested in. And what you do is you then take a laser, shoot it on your atoms or ions, and make it tune the frequency so that you can have the transition from a 2s to 2p, which is then followed by basically, experimentally, you need a muon beam and you need lasers. And you can do very precise measurement. So what is exciting about these systems is that you can extract the nuclear charge radii, and what is measured is this difference in the 2s to p, the Lampshift, with these lasers, and that is related to the radius via this formula. So that's the charge radius, which is what you want to extract. And if you have here a nucleus orbited by the muon, that will be the charge radius of the nucleus. So this works only if you know these other two terms, which cannot be measured, but or not directly measured, and they should be provided by the theory. So the first one is very well known. It's QED effect, it's the bulk of it, and it's known with high precision. The last one, it's called delta TP, stands for two photon exchange. It's a nuclear structure effect. It's not well known. So now perhaps most of you know this muonic atoms stuff because of the famous Protoredis puzzle. This is something that happened around 2010 when they first were able to extract the proton charge radius out of the muonic hydrogen measurement. And these are the points here, one measurement in 2010, another in 2013. And you see that what they obtained was a value around 0.84 femtometer, which is bigger than what was previously expected from electron scattering experiments or normal hydrogen experiments. Okay, so everyone was excited because this looked like potential lepton universality violation. So everyone started to look into that, and the situation today, it's this one here. So there have been a lot more experiments, and I think you could tell by yourself that this is quite scattered, but it's kind of like the most precise experiments are kind of leaning towards the small radius. So I think the community now agrees that the muonic atom measurement is correct. And whether you want to call this a full solution of the Protoredis puzzle or not, I think it's a bit of a matter of taste. But definitely what it seems clear is that at this point, it's not really that there is beyond standard model physics. Most likely all of this can be explained in a bit boring way by some unaccounted systematic uncertainties. Okay, so I'm actually more interested in everything beyond muonic hydrogen because, as you will see, it's just by looking at other muonic atoms where inside there is a composed nucleus that we could use our few body techniques to be helpful for this experimental program. And I would like to tell you here what has been done and what will be done from the experimental point of view. So the muonic deuterium has been measured and released, published on Science in 2016. The muonic helium-4 was measured and results have been published on Nature 1 year ago. The muonic helium-3 has been measured and is presently being analyzed. The muonic triton you cannot really do because it's radioactive. And the muonic lithium-6 and 7 are expected to be studied in the future. So what can we do from the theoretical point of view? It's actually to compute this delta TP, this nuclear structure correction, using a theory. And now I would like to tell you how we do. Is the audio and the slide right now? Or did you? Okay, if I don't see anyone complaining, I assume it is. So how do we calculate those? In order to explain you, I'm drawing here the system. So you have a muon that orbits around the nucleus that is made by several nucleons. What you do is you put yourself in the center of mass of the system, and you have your coordinates for the muon and your coordinates for the nucleons. So the Hamiltonian of your system will be made by a part that is the nuclear Hamiltonian that describes your ground and excited states. Then you have the muon Hamiltonian, which is the usual one, kinetic energy plus Coulomb force. The Coulomb force felt at the muon as if the nucleus were a point-like object. And then you have this delta V here, which is something that you can see as a perturbation. And that's basically the difference from the bulk Coulomb, and it's the interaction of the muon with each of the protons. So this guy is proportional to alpha, to Z alpha, so you can use perturbation theory to approach this problem. And if you use perturbation theory at second order, you obtain the expression for the two-photon exchange, which is supposed to be this Feynman diagram, where you have the nucleus in the ground state, in the initial state, and in the final state. And you have a muon, and in the intermediate state, in principle, the nucleus can be excited to any of its spectrum by the electromagnetic force, by this delta V. And G is basically the green function. So the details of how to calculate that, we wrote them in this review. I just tried to make the long story brief. So first of all, there are elastic terms that are called Zemach terms. These are those where the nucleus here remains in the ground state. And then there are inelastic terms that are those where the nucleus is excited. And as I told before, we call them polarizabilities. So there's these two divisions. And then you can also identify a part that depends on the nucleon, which we denote with N, and a part that depends on the few nucleon dynamics, which we denote with A, that stands for mass number. So actually, this is the part I want to discuss mostly. You can see, you can write it down as this, with this expression, where these ρ are transition densities of the charge operator between the ground state and the excited state of the nucleus. And this operator here, W, if you work it out, as said details in here, you can show that it can be written as a power expansion of a parameter eta, which, if you work it out using the uncertainty principle, you can see that it's roughly 0.33. So we truncate this expansion up to eta 4 because the next term is eta to the 5th and eta is relatively small. This should be, we hope it's enough. If it's not, we have to evaluate the leftover terms somehow. Okay, but I will show the results first done up to with this truncation. So if you work out a bit more, what you will see is that these polarizability effects can be written as a linear combination of special sum rules of the electromagnetic response functions. Something like that, where with special functions, I mean special sum rules, I mean that there are weights that are not the standard energy weight or inverse energy weight. The functions can be more complicated, such as logarithms, square roots, etc. And these are the electromagnetic response functions. So I don't think it's that easy to see it from here, but you can see it from this diagram in that you can imagine to break it in two. And then you would see that there are two equal parts that represent each like a muon scattering diagram on the nucleus, and that cross-section has to be described in terms of electromagnetic response functions. Then you get a sum rule because you actually have to close this diagram and you have the ground state in the left and in the right. Okay, so that's basically in a nutshell what this guy is. So we know how to calculate it, and there are various terms, and you see every terms we've given them a name. If you then calculate the elastic part, you also see that there is a cancellation. So if you want to calculate the whole two-photon exchange, you can save yourself the calculation of two terms if you want, but we calculate them each individually. So there are a lot of terms. The names are related to either this expansion in eta, that's the number 0, 1, 2, it's the leading order expansion, or the higher order terms. And the other letters are basically referred to operators. We have dipole, quadrupole, etc. The dipole, the first term, this delta 0 d1, is by far the leading term. And if you realize that, you could try to estimate this two-photon exchange from experimental data that give you information on the dipole strength. So actually, that's the first thing one would think of doing. And so I pulled up an old figure that I showed probably too many times, but this is helium-4 photoabsorption cross-section. That's a way to get a handle on the dipole response function. If you have that, you calculate a special sum rule and you have the leading order term of the two-photon exchange. So, but if you look at this figure a bit, you see, okay, experimental data have large error bars, and some of them are in disagreement with each other. So you already know that the value you will be able to extract will suffer from large uncertainties. And before really embarking into this, we already knew that in this kind of physics, somehow it happens that if you do a theoretical calculation, you can be more precise. And I'm showing here two calculations, one that we did in 2006, one that Sophia did in 2007 with two different Hamiltonians for the nuclear physics part. And we were getting two curves that very much on top of each other. So you have the feeling that the theory can be more precise, and that's why we decided to try to calculate this two-photon exchange purely from theory. And why do we bother to be precise? Because in this muonic atom business, this is all about precision. And the thing is that the measurement can be super precise, and the two-photon exchange, even though it's small, it's roughly just 1% of the whole Lampshift. It is not known with high precision, and that is presently the bottleneck to allow for a full exploitation of the experimental precision. And to show you that, I pulled up a table here that looks at the various muonic atoms, muonic deuterium, helium-3, helium-4, lithium. Here you see the uncertainties by which you can measure this Lampshift, so the experimental precision. And here on the other column, you see the uncertainty of the calculation of the delta TP. This is all before the Protoredis puzzle, and you see that the most precise one was for the deuteron, this work by Leidemann and Rosenfelder, and the other one are large uncertainty, typically at least one order of magnitude larger than the experimental one, and they were obtained by looking at experimental data. So that's not enough, and the experimentalists, of course, want to make use of their precision. So they need this delta TP with a higher precision. So now that's where we come into the game. Now we know how to relate this two-photon exchange to electromagnetic response function and sum rules, etc. So we can use all our knowledge in nuclear physics to solve the dynamics of the nucleus around which the muon orbits, and we do that solving the Schrödinger equation in the so-called ab initio way, with Hamiltonians that have 2 and 3 body forces, etc. And we use very well-established few body techniques, in particular the hyperspherical harmonics that work from particle number 3 up to 7. And then for the deuteron, we have used the harmonic oscillator. So I think it's getting very dark, but that's what it is. And maybe I try to turn on the light. Yes. So to compute these sum rules, we use something called Lampshift sum rule. It's just a generalization of what is typically done also in the many-body sector. We had to generalize it for the special sum rules that we have. And I will show you results that are either calculated with traditional potentials or with interaction from chiral effective theory. And in the very last part, I will show you what happens if we vary the chiral order to get a feeling of the nuclear physics uncertainties. So I will not say more about that, but now I go to show you some results so you get a flavor of how these things work. So as I said, there are various terms. We have to calculate them each individually. That's muonic deuterium, the lightest nucleus or muonic system that I want to discuss. And you clearly see from the graphics here that the delta D0 is the most important term. But the others are there, they just cancel. There is cancellation effect because some are positive or negative. And we calculate them with two nuclear potentials. And if we sum them up, This is work that we did in 2014. Then we were in agreement with the first calculation by Pahutsky, who is an atomic physicist. There were some slight difference that we understood, using something wrong with the isospin. And then eventually, around 2015, we agreed on almost everything. The slight, very tiny differences. So now this number was ready for the two-photon exchange to be used in the experimental extraction of the radius. So this is what was done by Paul and collaborators. They used our numbers as input, and they were able to extract the deuteron charge radius, which I plot here, and that's the result. It's always much more precise than anything else. And in this case, it didn't disagree with the electron scattering, but it was different from the code data evaluation. So I think what I want to point out is something else, that you can actually get an absolute determination of the deuteron charge radius also if you use the isotope shift from regular atoms. That usually gives you a difference from a reference from a reference atom. So you can get, for example, the difference between the deuteron and the proton. And then if you add the proton radius that was measured for muonic atoms, that's the point you get, the red one. So it was different from the absolute measurement of the Lampshift. And the difference can be solely attributed to the delta TP. So to this theoretical input, because in fact you can reverse this formula, and if you have a value for this and you measure that, you can say that you kind of measure the delta TP. So this difference of 2.6 sigma was a difference between the experimentally measured two-photon exchange and the theoretically calculated. And at the beginning, it didn't look so bad because the thing that was out there was the Protoredis puzzle, which was a 5 or 6 sigma effect. So 2.6 seemed small, but we thought that we have to investigate it further. And so we did. Instead of using just 2 models for the nuclear potential, we have used a lot of them, and we've done a so-called order by order chiral expansion. So this expansion now is regarding the nuclear force. We have leading order, next leading order, next leading order, and so on. And you see that while things are quite unstable or uncertain whether at leading order, by the time you are at next leading order, things settle down. And we were able to confirm the results we had before, still different from experiment, but now because we have used more models and we have this an uncertainty from the order by order expansion, overall our error budget has become a little bit bigger, and the puzzle went from 2.6 to 2 sigma. So then I have to say that other people also looked into that, and Pahutsky found out that there is a Z alpha to the 6 correction that is called the 3-photon exchange that you should not neglect. And one of his students, Marcin Kalinowski, also found out that there is a vacuum polarization correction that is of order alpha to the 6 that is large. And putting together all of these, eventually, at around 2019, there was consistency between theory and experiment, also for the 2-photon exchange. Okay, so I want to say something else for the deuteron, and that's the following. So as I hope I was able to convey so far, you can either try to extract these.
Sonia, 5
yes?
minutes, okay? 5 minutes.
Ah, okay, so then, yeah. You can either take, I have to speed up. You can either take data or, sorry, can you go away, please? Okay, so you can either take experimental data, you can calculate, and another mixed approach is to use dispersion relation, which are usually, I skip these, otherwise I don't get there, are usually like calibrated on experimental data. What we thought to do is actually to calibrate on theoretical calculation. And this is work that Vijaya Acharya did. I think he's there with you. So he can calculate very well these structure functions tested on experiment where experiment exists. And then we were feeding this to the dispersion relation. And what we got is actually, I think the relevant part is here. We got that before this, we used this hybrid approach, the uncertainty from the dispersion relation was very large. And while if you use this input from the theory, you can reduce it a lot. So I think that's the novelty of this, one of the last things that we've done. So in general, what I want to say is that by using this ab initio approach, we have really managed to shrink down the uncertainties by a lot. And this is shown, for example, in this plot that is a time-dependent plot of delta pole. The calculation in the 70s were not even at the beginning bothering with uncertainties. Then they were getting a value for the uncertainty because it was based on experimental data only. They were still large. And then we came and we reduced it by a lot. It's still, so that's the uncertainty right now, after the Protoredis puzzle and after we try to work on this, it's still not enough for the experimentalist. That has to be clear. So we need to find ways to reduce it, or at least to understand if it's possible to reduce. And there are various sources of uncertainties. There is a list here, and in the table you can see the percentage effect on every one of these muonic atoms. So I want to just spend a few more words on the nuclear model, how we try to do it better. And then if I have time, the Eta expansion, otherwise I skip that. So in the first calculation of the helium-4, we were just using 2 potential models. And now we would like to use more. And in particular, we did here an order by order chiral expansion. And the person in charge of this is Simone, a student who did this very nice calculation using the chiral forces from Gezelis et al. So they are local and they come at leading order, next to leading order, next to leading order. And you see here the chiral convergence of the delta TP. So this is complicated observable, but it does converge and it agrees with our previous estimate. But now we have a little larger uncertainty. So if the hope was to reduce the uncertainty, that's not what we obtained. It's clear that we need to go to higher order if you want to do that. And one last thing, so I mentioned there is a Neta expansion, so an expansion on a parameter, dimensionless parameter, that we truncated, and we ask ourselves how can we estimate the uncertainties, and there are various ways to do that. We tried recently to use Bayesian analysis to do that by making an ansatz on a prior distribution for eta and calculating a posterior by asking basically the data what this value should be. And out of that, then we could obtain an estimate of the truncation error, which turns out to be consistent with what we did so far for all the muonic system, but the muonic helium-3, which seems to have a problem. And I think this brings me to the conclusion that I think it was really clear that this ab initio approach allowed us to reduce the uncertainties. The experimentalists are happy about that, but they would like, of course, it to be more precise. And these calculations are absolutely important for them. And in the future, we'd like to look into things like the 3-photon exchange and potential erosion in the hyperspine splitting. That's interesting because it lets you look at magnetic properties like magnetic radii. And I would like to thank all my collaborators, in particular the young people that I mentioned, Vijaya, Simone, all the other involved that I had the pleasure to work with. And thank you for your attention.
Thank you, Sonia. Now, questions to Sonia? Okay, please.
Hi, Sonia, nice talk. So you showed that you estimated the uncertainty due to the chiral order expansion. Are there plans to estimate the uncertainty that comes from the uncertainties of the low energy constants in your chiral interactions?
Yeah, we haven't done that yet. Of course, that would be the next step. One has to build the machinery to do that. Yes, definitely that would be useful. It's not what is being done so far. So at the beginning, we just had 2 models. Now we have chiral order by order. And that's part of the story, definitely. Not the whole story. I think, though, what will happen is that this will increase the uncertainty, maybe potentially overestimate it. I think what one really needs to do here to be useful for the experimentalist to try to go to higher order in the chiral EFT, or potentially to try to constrain some of the radii in the fit of the chiral EFT parameters. That would be probably interesting to do.
Actually, this was done for the 2-body case, for the deuteron. There was a check taking assembly of possible higher EFT models, which are consistent with the experiment, which translate into the low energy constant, and the impact was checked, but only for the 2-body case.
Yeah, I think what the experimentalists would really like is helium-4 and helium-3. Helium-3 still has a large error bar.
And do you remember how large that error was compared to the chiral expansion? Were they similar or, smaller? I'll look it up.
No, we have it, I don't remember it.
Okay, please.
So I believe that when you do compare with different conversions to order of nuclear force, the first ingredient here is a binding energy, no? Correlations with a binding energy, which should determine the size of your system and impact. So if you remove this dependence on the binding energy, will there remain a strong model dependence?
So that's another thing that one can try. I think that will kill most of it. We wanted to try. We have not really yet had the best idea how to do that. But definitely, a part of these oscillations in this order by order expansion, it comes from the binding energy, because it's not correct here at leading order, of course. So all the study of this correlation, it's not yet included in this, and it will make the situation better. I still think that constraining the radii, it's also something that one should try to do. But it's not that trivial, because you have to do all these fits, and you have to have the machinery to calculate this delta TP, which are, as you see, made by many terms. They're not that simple observable, so to say.
Other questions to Sonia? Okay, Chris, please.
I had one myself, coming from an extreme novice point of view. So I hear this said that in the standard model, muons basically are identical to electrons. How strong is the experimental evidence for that?
Sorry, they keep coming. Sorry, I'm at home and.
Please, could you please repeat?
Yeah, I'll repeat the question.
Sorry.
So I hear this said, again, from the point of view, obviously, of a total novice in QCD and standard model. I hear it said that muons and electrons are basically identical. And I'm wondering, how strong is the experimental evidence for that?
Okay, so yeah, that brings me back to the figure, sorry that I have to scroll down here, the figure of the Protoredis puzzle. So when the situation was like this, there was kind of experimental evidence towards the contrary, that the electron and muon are not the same, and that is why people thought there is something beyond standard model that could explain it. But right now, the situation is this. So it's a complicated, scattered plot. But for those who are really deep into this business and understand all what goes into the various experiments, it's pretty clear that, well, you could drop completely this because there's super large error bar. You could look only at the muonic atoms and at the most recent either electron scattering calculation or ordinary atom spectroscopy, and that points towards the radius being small and towards not having any difference between muon and electron at this point. I think that the community
yeah, I realize, I mean, in the context you're talking about, this is true, but I've been hearing of other sort of 2 or 3 sigma cases in other reactions. I don't remember which ones that are being observed, I think at the LHC, where they're claiming some differences. But I'm just wondering, do you know what experiments show this identity and how convincing, how strong they really are?
Yeah, I might not be updated fully on this. The G-2 also has still a puzzle that needs to be understood that ties into this. But whether we can clearly claim it's strong evidence for new forces, you always find some models that can explain some experiments and not the other. I don't think I can say more than that, but yeah.
Neil wants to comment that.
The largest and more consistent problem comparing muons to electrons is the magnetic moment of the muon. There is some difference with what you would expect. There was an old experiment, and just last year, the Brookhaven, I think, repeated this experiment. They affirmed the old experimental result. More or less at the same time, there was a paper in Nature by some lattice QCD collaboration that they claim that they can explain this difference between experiment and theory by some hadronic loops that go into this calculation. But so I was very pleased, okay, the problem is solved, everything is okay, standard model is saved. But then I spoke with Raul here, and okay, he was here last week, and he's doing lattice QCD. So he said, okay, if you look better, then there is some controversy also within this community of lattice QCD about the quality of this result. So it is to some extent still open. It might be solved through these lattice QCD calculations, but this is the situation at the moment.
Yeah, this is this G-2 story. So at the end, I think it's fair to say that people are kind of converging towards thinking that if there are these puzzles, they are most likely explained with leftover uncertainties from the experiment, or also theoretical things still to be understood. While 5 years ago, it was more like it's certainly beyond standard model.
Well, any other questions? Otherwise, I will allow me to ask Sonia. Sonia, I understand from your answer to Himas that you have the binding energy correct. I mean, this due to the size.
At leading order, it's not correct. The binding energy gets correct around and next to leading order.
Yeah, because besides that, you still have this two-photon exchange that you have to go over, I mean, the virtual propagation of your system, no? And with the scattering states, I'm wondering how you can get a lot of precision, no, in the prediction for, at least for this part. I mean, if you know your charge distribution of your nuclei well, at one of the terms, okay, is fine, but and the rest. I was just wondering if this, how you could get, because for me this looks very, very complex to get precision on these contributions.
So what we did so far was just taking, well, first of all, derive all the formulas that get us to this observable, then take the forces and apply them brute force order by order. And we saw where we got the precision is not enough. So then if we want to go and have higher precision, we have to take into account either these correlations between the binding energy or the correlation with the radii. I don't know if this is the direction of the questions, the question that you were asking.
Yes, I mean, in part, I mean, the problem of the binding energy for sure is very important. No?
Yeah,
this will affect also the scattering states for sure. And okay, so you cannot estimate how bad is that for the moment, is you are saying.
No, I don't know, but I think it will get better. So I think the approach we took so far is, let's see how much uncertainty we have, because that was not even known before. Before we started to do this, the only calculation was done with one nuclear model, and then we realized, okay, there is dependence on the nuclear model. But now if you do this order by order expansion, which is what you should do in KITP, you realize that if the binding energy is not correct, then the rest also is not correct. So that's what we'll
you want to comment? Okay.
I think Federico misunderstood the point that was made. The point was that you can use the correlation with binding energy to further reduce the uncertainty. It's not a problem that we do not reproduce the binding energy at leading order, because within the uncertainty of a leading order calculation, because the uncertainties get progressively smaller as you go to higher orders, you would expect to get a large uncertainty at leading order in binding energy and in all other observables. So that's not a problem. So it's actually an opportunity rather than the problem that, since these observables that we are trying to calculate and predict, they are correlated with the binding energy, the idea is to then see if that correlation can be exploited to further reduce the uncertainty for the highest order that we quote.
So, but in that sense, I mean, you could, if you want, you could fix the binding energy. I mean, adding something to the three-body potential.
Are you suggesting like refitting the low energy constants of KITP?
Yeah, for example, because it seems, I mean, because this binding energy will affect more the large distance, I mean, structure that you have. Yeah. You want to comment? Oh, just wait.
Yeah, you just add some fictitious attraction to fix the binding energy with the same potential. And I guess you will reduce your error bus between the black one and the red one, which are two models, which also probably part of these two lines is also small difference in binding energy between N3LO and AB18 plus Urbana 9. I'm not sure.
We have to think whether that will unleash other sources of uncertainties in our calculations when you do that, but that's something that...
I think that Vijay is suggesting something similar. I don't know if it's doable to what I showed for the S factor, that you can see if there is a correlation between your calculated, corrections here and the binding energy, and see if there is a curve that is universal enough that you can conclude something and reduce the uncertainty, perhaps.
Yeah, that's the direction that I was thinking about. Thank you.
Further comments, questions? So I would like to thank again Sonia.
Thanks to you guys.